My name is Matt Roberts. As you probably saw on the website, from Cake Solutions, but we also were recently acquired. You'll see the branding in the bottom there. We're now part of Disney, and we're Disney Streaming Services, which is kind of cool and interesting for us. The talk is about implementing the Saga pattern with Akka, and we're going to focus on akka-persistence for the actual implementation, and then akka-cluster-sharding, if anyone's used that, for like the scaling. And just out of curiosity, how many people have used either of those two things? 1, 2, 3. Cool. Okay, and Tam, you don't count, sorry. Tam's from Disney Streaming Services as well. So that's really good. I'll assume zero knowledge, and I would really encourage you to like ask questions, heckle, and so on as we go, because like it's a meet-up, and I think it's always better if we have some audience participation. If you don't want to say anything, we can wait until the end though. And I also go really quickly, so if you need me to slow down, that's something you can ask, or you can watch it on YouTube at like half speed later, because that works as well. And I'll sound normal-ish on that. So I mentioned Disney Streaming Services, that's our new branding. Why should you believe what I'm about to tell you? We power Major League Baseball in the US, so we have like millions of users over there. I don't know any of them personally, but they really like baseball. We also power ESPN, which is a pretty big deal again in the US. I don't know much about it, but lots of users, lots of devices, and we stream lots of media to them. And then one I do know, Eurosport, so we have that in Europe, and that was also powered by our platform. We authenticate millions of devices and accounts in any given day, and then we stream media to them once they've successfully passed that authentication and obviously authorization. Most of the platform is written in Scala and runs on AWS, so it's pretty big, it's multi-region, multi-AZ, and yeah, it takes up most of my daytime. So before we deep dive into the solution using Akka, I wanted to just quickly describe the problem. I won't lie to you, this isn't actually how we solve the problem at Disney Streaming Services, because like if I told you that, our lawyers would be very unhappy, but this is just one way you could solve it with Akka. We leverage AWS services, and if you're interested to find out a bit more about that, you can talk to me afterwards. It's still a really interesting problem. So the product team came to us with what is effectively quite a classic requirement, and that's that an email can only be used once by a given user or account, and that email can be changed over time, but it can only be used once. So you can't have two people using the same email. That would be bad and not what the product team want. But as engineers, we had our own set of requirements, and that's that, like, okay, so if email can change over time, then that's not something we want our other services to reference, because it's distributed, and it would mean changing lots of databases in different places. So we don't want that to be propagated around the system, and we also want to be able to scale to an arbitrary number of users. And so, like, to understand what I mean by that, if we look at relational land, this is what you would do, right? It's nice and simple. There's a primary key, that's going to be our unique identifier that doesn't change, and then there's going to be the email, which is a unique index, and that does change. And the problem with that is that the unique index becomes increasingly expensive to maintain as your number of users grow. The obvious solution is to use like key value land, and that's nice and simple. So you just have your ID as the primary key on one table, and your email as the primary key on the other. But anyone who's done this will know that you then have a lack of atomicity, and that leads to inconsistencies, and you kind of have to deal with that in your application, which isn't much fun. Now that said, I think Akka makes it fun, so hopefully you'll get to the end of this and agree. So we'll look at how to implement the Saga pattern with akka-persistence in this part, and then, provided we have time, for part 2, we'll look at how you scale that out using akka-cluster-sharding. So persistent actors are just the same as normal actors, with one major-ish caveat. And by the same, I mean they have a mailbox, they send and receive messages, and they only process a message once at a time, which is really useful because then you don't have to deal with race conditions. The key difference is that you're going to be persisting events. So those persistent events will let you rehydrate the actor if it crashes, or if you choose to terminate the actor because you don't have enough memory in your JVM. So these are like the possible states that the user actor and the email actor that we're going to implement can be in. Now, we'll look at the email actor first because it's really simple, as you can see, in comparison to the user actor. But the email actor just has two states, right, which is email created and email deleted. The user actor is much more complicated, and it's quite hard to understand, I think, in that form. But if we look at it this way around, you can see that there's a client who's literally like an end user on their phone, and they're going to like use HTTP, for example, to hit up against our API. And then that API is going to hand off to the actor with a register command, and then the actor is going to basically persist an event to the user journal saying that the registration has started. Then it's going to send a message to the email actor saying, hey, create an email for that user. That actor will then persist an email created event to the email journal, and then finally reply saying, yep, that's all done. And then the user actor will finish the saga with registration succeeded, and then finally 200 OK the user. The slight issue is that there's like some error cases that could come in. So the registration might start, the email already exists, and then the saga would fail. And that's okay because we'll have the events persisted to the data store, so we'll know that someone tried to use an email that already exists, and we can just 4xx the person. And then the other option is that we have like a network outage and we don't actually persist anything to the database, and that's kind of like unfortunate, but we'll 5xx the user, and we'll be able to tell that either there's no event in the data store, so nothing happened, or we'll see a registration started and we'll know that's orphaned, and because we never saw the registration succeeded, we can clean things up. So, like I said, the email actor, really simple. I say that, there's the protocol for the email actor. So I've been talking about sending commands, I've been talking about replies coming back, and I've also been talking about events getting persisted. It's a lot to take in, so let's like critique that code and hopefully help you understand it as we do that. So the top there, I just put some type aliases in. That's me being really lazy. What I should have done is use like any vowels, because then I would have got type safety. As it is, it still makes the code easy to read, so you'll know when something's an email or when it's a user ID, but it doesn't really help you get the most out of the compiler, so like any vowels would have been much better, but moving on. This is the command section, so these are the commands that we're going to send to actors. Those commands are going to then result in events being persisted and also replies being sent, which we'll see. What do those commands look like? Kind of big. There's an email, there's a delivery ID, and there's an actor ref, and there's some user info. The thing that's a little bit strange is that delivery ID. You'll probably be thinking, why has he done that? And the reason is that, unfortunately, because the actor that's going to call this is using at least once delivery, I have to have a delivery ID so that I can then check that the delivery actually happened. If it didn't, retry it, which we'll see in a second in the implementation. And then there's also this client actor ref. And that's there because I want to make sure that if I lose the user actor, I can still send a response to the correct person, which is the person who invoked the API. So without that actor ref, I don't know who the end client was. Now you might be thinking, why do I put that in the messages? And the reason I put it in the messages is because now I don't have to persist it into events. So like, the events are the thing that are going to live in the database and they're going to live for a long time. So you really want to try and keep the events as clean as possible, and then make effectively your commands and replies a bit messy because they're temporary and you won't have to like look at them for a long period of time unless you're debugging, then you might have to look at them. And then email replies, so I kind of mentioned this, but like there's the delivery ID and the actor ref again, and that's just so that it goes into the email client, email actor, and it comes back out again. And then I mentioned email events, so either the email will be created or an email will be deleted. And that's nice and easy, and these look really clean, so it's just the user ID and the email. So we've just created our reverse lookup index, and that's how that works. And then finally, there's the state of the email actor. So the email actor itself is going to maintain some state, and it's kind of like confusing, but the events are what persisted, and then we recreate the state from the event. So it's event sourcing effectively, even though it's not explicitly like stated in the like actors that we're going to inherit. So looking at the implementation of the email actor, there's quite a lot to take in, so we'll just go through it bit by bit. First thing is this. I'm setting a receive timeout, and when I get that receive timeout, I'm going to terminate the actor. And the reason I do that is because all of the events have been persisted to the data store. So I can do that and know that when I rehydrate the actor using the receive recover command, that basically I'll be able to recreate the state, so I can safely take stuff out of memory without worrying about it. And that's one of the key differences between like an actor and a persistent actor, is that you can kill off the persistent actor pretty much at any time and reclaim that memory. which obviously helps from a scalability point of view. And then there's this other weird thing, which is also an artifact of using a persistent actor, which is I have a persistent ID, and that is what is actually going to be used to key off in the database. So the primary key of your No-SQL implementation, whether it be Dynamo or Cassandra, that's the column that you'll see in there. So you'll see like email and then the actor path, which is actually going to include a UID, as we'll see later on. And then finally, there's the state. So this is state that's held in memory. It's not persisted at any point. And then we update that using an update method. And we just do that to keep the actor as dry as possible. And it's a really simple implementation, first implementation of the evening. It matches on the event, and it says, hey, if it's an email created, then set the state. And if it's an email deleted, clear the state. And it's that simple. So not very functional, but it gets the job done. And then the next thing, so now we know how to update our actor state. Now we have to handle receiving a command. So this is where most of the business logic happens in a persistent actor. So you can see the first thing we do is match on the state. It's kind of arbitrary, you can do it both ways around. Match on the state, and then based on the state, we decide whether or not the command is correct. So for example, we see that we get a create email, we match on the state. If there is some state, and the user ID equals the same as the user ID in the message, then we know we've just received a duplicate message. And that's confusing when you first start using at least once delivery, but with at least once delivery, you have to handle duplicates on the recipient side. So I assume here that if I see the same user try and create an email twice, then it's just a duplicate message, and I can say, okay, it's created, you're good, and there's no error handling going on there, so it's idempotent, as long as you don't get any other messages in between. But if the email is there, so there's some state in our actor, but the user IDs don't match, then we know there's a conflict, and so we'll return an email already exists. And then the nice and easy case is there is no state, so create the email record in the database. That is a duplicate slide, quick check. Yeah, it's just delete email, which is exactly the same, so we'll skip that. Then we get to the receive recover. So receive recover is a bit strange. I keep talking about like rehydrating an actor or replaying events to restore its state, and that's the responsibility of this method. And in the email actor, it's really simple. All it has to do is call the update method that we saw before. So it's really, really simple, the email actor. It gets much more confusing in the user actor, which is responsible for managing the Saga, as we'll see, and that's a result of at least once delivery. So yeah, I think I summarized it pretty well. Complex, persistent actor with at least once delivery. It's kind of unfortunate, but it's part of using Akka is that you have to deal with this complexity yourself. So you can see the box is a lot bigger. We're going to start off in this unknown state. Then we'll either go to registration started for sure. We'll either then fail or we'll go to succeeded. Once we've succeeded, we can then go into these change email states, which I'm not actually going to show because it's so much code it won't fit on the slides. But trust me in that it is exactly the same as the first step, just with one extra step to do the kind of bait and switch of the email address. If you're interested in seeing the whole thing, I intend to do a couple of blogs on this with all the code and just talk about some of the pros and cons of doing it this way in a bit more detail. So the protocol looks exactly the same. Something I didn't mention when I looked at the email actor is I really recommend if you're using actors, put all your protocol in one companion object, because then you know exactly where it is. And obviously, typed actors are coming and they're kind of pretty well supported now, but for persistent stuff, I'm not sure how it plays. So, if you're going to use persistence, then just make sure you put it all in one place. The only thing that's really changed here, which is kind of interesting, so it's very similar in terms of there's commands, replies, events, and user info. The big difference is there's a couple more events. So there's the registration started, and then it's either going to go to registration failed or registration succeeded. And again, the interesting thing about those events is that now we have this delivery ID. And you remember that for the email actor, I said don't put delivery IDs in your events unless you absolutely have to. This is one of those instances when you have to. It's kind of unfortunate because then it's persisted and you don't need it other than for resending that message. but it makes everything work. So, and there's the reason. So that's the at least once delivery trait that we mix in, and that means that when we update our state, that when we're in recovery mode, which Akka hides from you, and you just have to accept that when you're in recovery mode, that messages with an unconfirmed delivery ID will not be resent, will be resent. So only ones that haven't been successfully delivered to the other actor will get resent during recovery, which is a little confusing, but makes sense when you look at the implementation. So this is the implementation. So we're updating our state based on a user event. That user event could be registration started, registration failed, or registration succeeded. And unfortunately now, the update method is very side effecting. So we're going to use the inbuilt akka method called deliver, which basically says, hey, the registration started, so deliver a create email if the delivery ID has not been confirmed. And that's pretty wild, but it does work. So we're only going to send create email if at the end of the recovery we haven't seen that delivery ID confirmed in either the registration failed or the registration succeeded. So you can see, I just realized my cursor isn't working, which is embarrassing, but this is me confirming the delivery here and here. So all of this will get executed. The reason this goes in the func is because then it's lazy and Akka can cheat and basically not send that unless it hasn't been confirmed. And so that's like possibly the most confusing thing when I did this. I was like, that's confusing, but it is quite well documented, so you can work it out. But it makes reasoning about at least once delivery actors really confusing. And we'll see, I do a critique of my work near the end. And that's one of the things that I try to solve for. So receive recover, much more complex in this actor. Receive command, so receive command is actually pretty straightforward. I won't show you the implementation of sol and hash, but just assume that it is going to sol and hash that password and then give you the result. And then basically just persist the event, which is the registration started, and then call the update method. So a little bit confusing, but obviously that's a function update, and we're going to pass in the event. Persist second argument set takes the function and passes the event in. And then for email already exists, then we know to return to the client, which we put in the message. We can say, well, that registration failed, so that's that happening there. So client comes in, and then we can reply to them. And then for the email created, so that's a success, so we can say registration succeeded back to the client. And obviously, at each point, we update with the latest event. And it's a little bit weird. You can see, actually, so this is the shorthand, and this is me exploding it. So I persist the registration succeeded event, and the next set of arguments is an event goes to update event. So that's like the longhand. Glad I put that in there, because that's pretty hard to understand if you don't know what's happening. So yeah, ignore that. So at that point, we'll pause, because I might have lost a few of you, and give you an opportunity to ask questions. So that's how you do the Saga pattern. And at that point, it's pretty good, right? But there's a few deficiencies, and I just wonder, can anyone like point out what the obvious deficiencies are? See if you can predict my future slides. No? Everyone happy with that code? Some nods. Okay, not to worry. Well, the code is a little problematic. Let's look at why. So let's imagine we've just got 3 users. We're not a very successful startup. We don't have millions of users yet. We can manually create the actor refs for those for the email actors, and we can do the same for the user actors. So like email actors, nice and easy. It doesn't need to know about any other actors. So there we are passing the emails in, and we're going to get back an actor ref. You could factor this out and have like Alice props, Bob props, and then pass the props to the ref, to the actor off to get the ref. And then this one's a little bit more complicated. The user actor needs to know about the email actor so it can send the messages to the right place. But at that point, once you've done that, you can look up those actors without knowing where they are or by referencing their constructors explicitly. So you can use this actor selection to say, hey, and I told you about the actor path. So here's the actor path for email, and here's I didn't put the full UID in, but there's the actor path for the users. And so you would get the actual actor rest back, and you could send them messages, and it would all just work. And that's what it would look like at runtime, kind of in memory, is that you would have your JVM, and you'd have these 6 actors, and the user actors would know about the email actors. And that would just work, and they'd drop out of memory eventually. But obviously, if we had millions of users and maybe small instances, then we would probably run out of memory really quickly, even with taking the actors out of memory. We'd still probably hit a point where we couldn't handle enough concurrent requests. And that's where akka-cluster and akka-cluster-sharding aims to kind of like help out. So with akka-cluster, you have to solve load balancing yourself. But obviously in AWS, you can just put an application load balancer in front of your app, as long as you're exposing either a HTTP or TCP API. And then you can start multiple nodes, is what Akka calls them. You can start multiple nodes. They'll all start gossiping over TCP. You can see A, B, and C are all talking to each other. And obviously, because we're using akka-persistence, they'll all talk to some shared data store, almost always over TCP, like Dynamo, Cassandra. I think you can even use Mongo if you want. Does anyone use Mongo? No? Yeah, cool. That might be the answer. And then at that point, obviously, you can have a lot more of those actors in memory, which is really useful, and obviously means you can scale horizontally. So akka-cluster-sharding takes that like a step further. You saw me manually like construct the actors and their paths. Actor-sharding does all that for you. So it'll auto-magically instantiate users and also the email actors in the correct node in the cluster. And it does that by sharding on the key that you specify, which we'll see how to do in a second. And then the only other bit of magic left is this singleton. So there'll be a user singleton, and there'll also be an email singleton. And that singleton is responsible for detecting when a node is down. So akka-cluster is dynamic in that if we lost, for example, node A, the singleton would know that that shard region can no longer be running on node A, and move it to node B and reshuffle. And so that's really useful, because obviously in reality at big scale you'll lose instances semi-regularly, especially if you're on AWS, because they kind of intentionally don't provide guarantees, so you're forced to be horizontally scaled. So how does that work? It's actually, once you know how, it's really simple, and it's pretty well documented again. So you use this extension method, cluster sharding, which you just pass the system to, and then you can call start, pass in your type name, which is going to be used in the path of the actor, and you can also, you pass in the props. So I mentioned earlier when I manually instantiated them, I could have like taken the props and put it elsewhere. And that's what I'm doing here. I'm saying, hey, here's the props for the email actor, which basically tells Akka how to instantiate an email actor. And then I have settings, which is the cluster sharding settings default. So that line is just an unfortunate consequence of the framework. And then the important thing is that I tell it how to extract the ID and also how to shard, so how to take an ID that we've just extracted from the message and shard it. And with just that, Akka is able to do everything else for you auto-magically, which is really, really useful. So what do those two methods that I pass in look like? So the first one is the ID extractor. So that basically says for any command that we're going to send to that actor, how do I get the ID, which in this case is an email, because it's an email command. So that is just a function that goes from command and returns the ID, email, and the command itself. And then shard resolver, a little bit more complicated. Given an email command, then it has to just create like a number. It goes to a number, it has to be an integer. Oh no, it's a string, sorry, that's a lie. I use a number because it's easy to reason about. And basically that will be then used to decide which shard region a given email lands in. And so and you have to use consistent hashing. So I just take the absolute value of the hash code of the email string, modded by 50, which means I'm going to have a total of 50 shards, which is actually a really low number, so don't use that number. I use 50 I actually used 5 in the original example, I think, when I presented this internally. And then you can see all your shards really easily, and you can see what happens when you take out a node, because like a whole shard will move, and you'll easily be able to populate each shard with fixtures. But when you're in production, you want to be like at least 1024 or 2048. But there is a trade-off there, because the bigger the number, the more shard regions you have, and so the more shard regions you have, then the smaller the number of a given actor you're going to have in each region, and then that can result in a bigger reshuffle than if you just had a few big ones. And so that was the email factory, and it stands to reason, given that the email actor was simpler than the user actor, that the user region factory will be slightly harder, but it's not too bad. We pass in the email region that we just created, or just provided a method to create, and then from that, the cluster sharding again can just create the user actor. And this comes back to like one of Akka's like fundamental concepts, which is that actors should be like referentially transparent, so you shouldn't know where the actors are. So the fact that these actors are secretly behind this big add-on cluster sharding that does all this work for us doesn't matter. As far as this function is concerned, it just always gives the right email for a given email address. And again, as before, we pass in these 2 helper functions. In this case, because it's a user, the user ID is going to be the ID that we extract from the command, and then the shard result is exactly the same, just doing mod 50, so you can actually like print out a table of the shard regions. So there's only one thing I skipped out. How am I doing for time? I'm nearly out of time. So I'll quickly whip through the evaluation and we'll do questions. There's 3 main issues with what I presented. You might have spotted it and just been too nice to say. User actor does 2 things. It does the registration saga, and it does user persistence, and that means it's more complex than it needs to be. The second one is that like side-effecting actors are really difficult to test. Like when I presented this internally, immediately someone was like, how are you going to test that? And he's right, like it's really hard to test. And also the final one is that akka clusters are hard to run operationally. I didn't really give anyone an opportunity to raise that as a flaw. The first issue is pretty easy to address. So that's what it looked like as I originally did it. That's what it should have looked like, but I just didn't spot that immediately. So now there's a registration actor that looks after the saga. There's a user actor that is solely responsible with creating a user, and there's an email actor that's solely responsible with emails. And then the at least once delivery complexity is purely the responsibility of this actor, and everyone else can use nice and easy persistent actors. I say nice and easy because persistent actors can be very easily expressed as like a pure function, where you basically, a little bit confusing, but that handle function there takes a command and some given state, and then it returns events that need to be persisted, state that is the new state, and a reply, which is the reply that you're going to send back to the actor. And once you've done that, testing is really trivial, because like you can basically exercise all of the cases without worrying about akka at all. So the akka completely drops out of the equation. You can unit test everything, and the fact that you're persisting stuff becomes like a non-issue. And that's really useful, obviously, for giving you confidence that your like state machines are correct. And then the final critique is that like I showed you this cluster member node C, which has that singleton on it. If that gets taken out, then your time to recovery is normally like at best seconds, at worst minutes, which obviously means you're going to have a bad day from an operational perspective. And I ran over by 2 minutes, so sorry about that. But any questions? And thank you for listening. I hope it was useful. And all that code will be made available.